Okay, in today's lesson we are going to talk about exponents and then operations on variables that have exponents and the expressions combining and simplifying. As we go through this, I'm going to take probably more time than I would normally take to do a lot of small, quick examples, because part of doing this is understanding the logic behind why the operations on exponents are what they are and what they mean, and how do we look at those things. We'll get deeper into this in the Algebra 2 course, but I wanted to review with you some of the basics, and as we go through the examples, we'll see how they relate to the properties that we're going to use. Okay, so first thing is, let's go to this page. And the first thing here is when we multiply like numbers or variables. Now, I mean, when I say like numbers or variables, I'm saying it has to be the same variable representing the same value. And then if we multiply these variables with exponents, we add the exponents. So as you can see in this red example, z to the a times z to the b equals z to the a plus b. And then over here on the right is another example, m to the 6 times m to the 8th equals m to the 14. M to the 5th times m to the minus 4 equals m. Okay, so we're adding 5 and minus 4. When we add 5 and minus 4, of course that becomes a subtraction, and we're left with m to the 1. Now, we do not write the 1. If we see this written like this, this is actually m to the 1 here, which we write as just m. We don't write the exponent 1 when we have it. Okay, the third example on the right, a cubed times a to the minus 5th. We're taking 3 and we're adding minus 5. That becomes a to the minus 2 power. And we're going to see another property here in a second, which we call the reciprocal property. And I've written that in green, where a to the minus 2 is equal to a 1 over a squared. Okay, and we'll talk more about that in a little bit. Okay, but that's the first basic property, is when we multiply numbers with exponents, we add the exponent. When we divide like numbers or variables with exponents, we subtract. So multiplication is add, subtraction, or division is subtraction. So if we have in the example here, a to the m divided by a to the n is a to the m minus n. Okay, so the example in red over on the right, b to the 8th divided by b cubed is equal to the b to the 8 minus 3, or b to the 5th. Now the same thing would apply with negative exponents. If we're subtracting a negative, we're actually adding. So just for the fun of it, let's do another real quick one here. We could do b to the, and I'll make this one, let me change colors here. So if we had, for example, b to the 3rd divided by b to the minus 5th. Now, you would normally not write this kind of expression with a negative exponent in the denominator, and we'll talk about that too in a little bit. But anyway, just for the sake of illustration, we would have b to the 3 minus, 3 to the minus a minus 5. So that would be equal to b to the 3 plus 5, or b to the 8th. Okay? And let's see, the third property, we can use the reciprocal property to change the sign. Now, a lot of times when we're doing math, they may have in the instructions, please don't leave any negative exponents in your answer. Right? So how do we do that? Well, p to the minus w in the example here is equal to 1 over p to the plus w. Okay? So if you had, for example, let's say we have, well, I'll just go ahead and use a number for this. Let's suppose we had 2 to the minus 4th. Okay? 2 to the minus 4th, we could rewrite this as 1 over 2 to the positive 4. Okay? And so what would you end up with here? Well, you'd actually end up with a fairly small fraction, large number in the denominator, but small fraction. So we would have 1 over 2 to the fourth. Well, 2 to the fourth is 16, right? So 2 to the fourth is 2 times 2 times 2 times 2, which is 4 times 4 or 8 times 2, whatever. And so we have 1 over 16. So 2 to the minus fourth really is 1/16. Seems a little weird, but that's the way it works. And we'll do some illustrations a little bit later on when we kind of put these things all together. Okay, so that's the first three major properties. All right. Okay. So let's look at a couple of special cases of exponents, and you may remember these. And mathematically, they make a lot of sense. I'm not going to go through the analysis of that with this little video, but if we have a, say, to the 0, anything to the 0 is 1. Okay, anything to the 0 power and I want to stress that this really does mean anything. So any number, any variable, any combination of things which end up with a to the 0 or a variable or a number to the 0 power is 1. Okay. Now the mathematical definition that gets you here, like I said, I don't want to go through right here for the sake of time, but it actually is mathematically correct. All right. It's not just somebody's saying how do we deal with this a to the 0 thing. So for example, let's suppose we had a to the minus 5 times a to the 5th, right? Okay, and what would we do? Well, we would have a to the minus 5 plus 5, okay, which is the addition property, and what does that equal? It's equal to a to the 0. And so we know the answer to that is 1. Another way we could write this using the reciprocal property is, let's suppose we change this a to the minus 5 using the reciprocal property, okay? And so that becomes 1 over a to the 5th times a to the 5th, right? What does that equal? That equals a to the 5th divided by a to the 5th. And it doesn't matter what number a represents. What we really have here is what? 1. Okay, so mathematically, you can rest assured that a to the 0 is in fact 1, or any variable, any number to the 0 power is 1. The other example is the exponent 1. Okay. And I won't go through the lengthy thing that we did here earlier, but a to the first power, or a to the 1, is just equal to a. And we kind of went through that a minute ago with one of the other examples. A to the first power just means the number is what it is, okay? And so that's one reason we don't write the exponent when we have a to the 1, because it's understood that property exists. Okay, so a to the 1 equals a, any other number as well. Okay, so I guess I call these special cases because they do come up from time to time, and some people that don't understand exponents very well kind of scratch their head and say, why is a to the 0 or b to the 0 or anything else to the 0? Why is that equal to 1 instead of 0 or something like that? Okay, all right. So let's do a little bit of work here on why the addition property, subtraction property, and reciprocal properties make sense. We're going to take some very, very simple cases. As you probably know with exponents, anything that you start raising to a power gets into some large numbers very quickly. So we're going to stay with some pretty small numbers here, like 2 and 3, just to illustrate our thing. Okay, so let's take the number 2. That's an easy one to do. And everything binary, like computers and everything else, are based on a base 2 mathematical system. So let's say we have 2 to the 3rd power times 2 to the 4th power, right? And we say by the rules of exponents that this is actually 2 to the 7th power. Okay. Now, you could take a calculator if you want to and work that out. And I think what we're going to find out that is, let's see, 2 to the 5th is 32 times 4. What is that, 100 and, let's see, hang on a minute. All right, so that's 2 to the 5th is 32, and we're going to multiply that. That's 128, right? Okay, if I put that in the calculator, whoops, I'm sorry. Let me rewrite that more clearly. 128, all right? That's 2 to the 7th power. And then, so let's just take these two numbers. So what's the 2 to the 3rd, okay? 2 to the 3rd is 2 times 2 times 2, which is 8, okay? And 2 to the 4th is 16. So 2 to the 3rd times 2 to the 4th becomes 8 times 16. If we multiply 8 times 16, what will we get? 8 times 6 is 48. 8 times 1 is 8 plus, and carry 4 is 12, 128. And there you go, okay? So you can see that in this illustration that the addition of exponents when we multiply numbers is mathematically correct, okay? Let's do another one here. Let's try something like, what about 2, what if we have 2 to the 5th times 2 to the minus 2, right? And this, with exponents, that's going to be 5 plus a minus 2, which is 2 to the 3rd, right? And 2 to the 3rd is 2 times 2 times 2, which is 8, right? So let's see what happens. So 2 to the 5th is 32, and we're going to multiply that by 1 over 2 squared using the reciprocal rule, right? So that's 32 times 1/4. Well, what's 1/4 of 32? It's 8. All right? So the reciprocal rule and the subtraction rule are working there for us. Well, that's actually mostly the reciprocal rule. Let's take a look at one where we're using the subtraction rule. Okay, the subtraction rule, let's do, let's say we do 3 to the 4th divided by 3. Okay, so what is that? That's actually, and I'll write it in here, even though we don't normally do this mathematically, that's actually 3 to the 1, right? So that's going to be equal to 3 to the 4 minus 1, which is equal to 3 cubed, which is equal to 27. 3 times 3 times 3. And so is that true? Well, okay, let's take a look at this problem worked out beforehand and then see what we get. 3 to the 4th power is, well, let's do 3 to the 1. That's easy. 3 to the 4th power is 9 times 9 is 81, okay? And so 81 divided by 3 is, guess what? 27, okay? So this is the illustration of the subtraction rule, okay? So these are just simple illustrations to show you that mathematically that is in fact working. Let's see what our next thing is here. I may throw in some examples here. Yeah, okay. Let's throw in these examples. Let me go here and get this thing out of the way a little bit. Okay, there we go. Okay, back to our pens. All right, so let's take a look at just some random examples. All right. All right. So we're going to simplify some expressions here. We haven't talked about the power rule yet. We'll cover that in just a minute. So, okay, 14 to the 0 equals, what did we say? Anything to the 0 power is 1, right? 14. 4 to the minus 3. Same thing, reciprocal rule. 1 over 4 cubed, which is 1 over 64, right? 4 times 4 times 4. 4 times 4 is 16 times 4 again, is 64. Okay, 4 to the minus 3. Okay, what about, let's see, 1 over, here's a good one, 1 over x to the minus 9th. And we don't know what x is, but we do know by the reciprocal rule that this is going to be, we basically, and just for simplification, I call this taking it upstairs, okay? So what we do is we take this x to the minus 9th, and the flip of a reciprocal is we take what's in the denominator, put it in the numerator, and I call that taking it upstairs, okay? Downstairs and upstairs. So we're going to take this upstairs, and that's going to become x to the positive 9, all right? And then whatever x represents, we could raise it to the 9th power and so forth, okay? So what if we have, let's do a couple more here. Let me create another empty page. Let's do 14 squared times 14 to the minus 2. Okay, we'll show this 2 different ways again. But first of all, this is going to become 14 to the 2 minus 2, which is 14 to the 0, which equals 1. And what if we did this with the reciprocal rule? What if we had 14 instead of the addition rule? 14 squared times 1 over 14 squared, which is equal to 14 squared divided by 14 squared, which is equal to 1, right? So you can approach a lot of these problems in more than one way. What about x to the 8th divided by x to the 14th? Okay, we're going to use the subtraction rule here, and this will be x to the 8 minus 14, which is equal to x to the minus 6. And we said we don't like negative exponents normally, so we would rewrite this as 1 over x to the 6. Okay? And let's see, what else have I got here? Let's do, okay, here we're getting a little bit more complicated here, but it's not really a big deal. Let's do x to the 5th. Well, that one, yeah, I'm looking at a sheet of paper here. All right. Let's see. Yeah, all of these are a little bit wacky. Let me just do a couple. I'll make up a couple of them here. Suppose we had x to the 3rd times x squared times x to the minus 4, and we're going to divide that by x to the 5th, right? Wow, okay. So is this hard? No, it's not. Just take it one step at a time. First of all, let's combine terms up in the numerator, right? And so that's going to be equal to x to the 3 plus 2 is 5 plus a minus 4, okay, is just x, right? X to the 1 or x. Because you've got 3 plus 2 is 5 plus a minus 4 is 1. And then we have x to the 5th. X to the 5th is kind of funny looking x there. Let's see if we can do a little better with that. X to the 5th. And now we're going to use the subtraction rule, right? So this is x to the 1. Remember, this is x to the 1, even though we don't write it that way. So then we're going to have 1 minus 5, which is going to be x to the what? X to the minus 4, right? And we would then rewrite that to, if we had an instruction that said, I don't want negative exponents, then we would write this as 1 over x to the 4th, okay? All right, now let's look at this a different way. Let's just as an illustration here, what happens if we look at this clump right here? All right, technical term, clump. Okay, x cubed times x squared is x to the 5th divided by x to the 5th. And so all that is what? X to the 5th divided by x to the 5th, which is 1, right? And times x to the minus 4. So we would actually have 1 times x to the minus 4th, which is equal to 1 over x to the 4th, right? Guess what? Ta-da! All right. Fun with exponents, right? Okay, so there's more than one way to approach many of these, and we're going to do a little bit more scrambled up example in a little bit where we combine all kinds of things and show you just how to take it step by step, one thing at a time, so that you don't get too messed up. All right, let's see. What did I have on this page? Okay, 1 over z to the minus 3. Okay, we talked about that already. Okay, let's see. Where did I get? Oh, okay. This was just another illustration of the reciprocal rule, showing that, you know, if we wanted to put b on top instead of a on top for this one, we would have to do the reciprocal rule for both of them. The a cubed would become 1 over a to the minus 3, and the b cubed in the bottom would become b to the minus 3 on top. Just illustration of that. All right, so let's see what's next here. Let's see. Oh, okay. Oh, wait a minute. I'll come back to that in a minute. Let's see. Okay, yeah, the next thing I wanted to talk about, okay, before we get to this page, all right, let's go back here. I want to clear this page. I wanted to go over the power rule, okay, the power rule. In the power rule, just like when we add exponents, when we multiply two numbers, if we raise a power to a power, all right? So let's say we've got m cubed raised to the cubed again, right? M cubed raised to the cube. If we have this, we call this the power rule because we're taking an exponent and raising it to a higher power, okay? So here's our initial exponent right here, and here's our raising to a power. So what do we got here? What we do here when we have power to a power rule, what we do is we multiply the exponents. So this becomes m to the 3 times 3, or m to the 9th, okay? So does that make sense? Let's look at it a different way. Let's look at it building it up from the addition of exponent rule. So what if we had m cubed? Well, what do we got? We've got m cubed times m cubed times m cubed, right? So we take this m cubed base and we're going to raise it to the third power, so we're multiplying it 3 times, and we get m cubed times m cubed times m cubed. If we now use the addition rule, what do we got? 3 plus 3 plus 3 is m to the 9th, okay? And that's exactly what we have here. So the power rule says that when we raise a power to a power, we will multiply the exponents. Now, one of the things we have to be a little careful of when we're using the power rule is that if it's in parentheses, like it is here, okay, and it's raised to a power, we have to raise everything inside the parentheses to that power, all right? So what if we had 2r squared to the 4th power, all right? Well, what do we got to do? We have to raise the 2 to the 4th, okay? So it actually becomes 2 to the 4th because it's inside the parentheses, times r to the 4 times 2, which is 8th, all right? Now, if we have a number like this, we usually go ahead and evaluate the number, unless we're told not to do that. So I'm just going to make a cleaner looking 8 here. All right, so 2 to the 4th, r to the 8th. Well, what is 2 to the 4th? Well, 2 to the 4th is 16. All right, so it's 16 r to the 8th, and that would be our final answer. Okay, so don't forget that when you have anything inside a parentheses which is raised to a power, everything inside that parentheses has to be raised to a power. Now, let's do one more. Let's do like if we had 3 different things in there. Let's suppose we had 3 a squared b to the minus 2, all raised to the 3rd power. Okay? Okay, so what do we have? We have 3 cubed, a to the 6, and b to the minus 2 times 3, b to the minus 6. Okay? Now let's rewrite this. First thing is, the 3 is a number that we know, so we go ahead and raise 3 to the third power. We said 3 to the third power is 27. 27, and then we have a to the 6. And what do we do with the b to the minus 6? Well, if we stick by our normal etiquette rules of math, we say we don't like negative exponents, so we would use the reciprocal rule and take the b to the minus 6 downstairs, and it would become b to the positive 6. Okay? So think about that just for a minute and make sure that makes sense to you. But remember what we did there. Don't forget anything that was inside the parentheses, we go ahead and raise that to a power. All right? Okay. So let's combine all these things now into some problems that, if you were to look at them 20 minutes ago, may have seemed rather strange to you. But let's read this first, and then let's work some examples. It says, when simplifying exponential expressions, calculations are easier and have less chance of error if we line up the variables so we can simplify each variable separately. So let's suppose we had a b, a c, and a d variable and a couple of numbers in there. We would try to put all the numbers either together. Well, let's say it this way. Put it together in the numerator and put them together in the denominator. And then what we would do is we would execute the various exponent operations for each variable separately and then see what we end up with. Okay, so let's just see what that looks like. Okay, and just a reminder here that good math etiquette is usually to avoid negative exponents. Okay, so we're going to keep that in mind as one of our rules. Okay, suppose we have, let's say we've got 2 b cubed c to the minus 4th times, and we won't get too complicated here, let's say times 3 parentheses 3 b c squared cubed, okay, all over b c, okay, squared. Okay, wow, that looks weird, right? Okay, so first thing, just like any order of operations problem, what do we do first? What's the PEMDAS thing? Okay, let's take care of the parentheses first. And so what we're going to do is we're going to write this as 2b cubed c to the minus 4th, and then we're going to go ahead and distribute, or to go ahead and use our multiplication of exponent rules and take care of this. Okay, so 3 cubed, right, is times 3 cubed, and I would write 3 cubed here, or I could write 27, really doesn't matter, but let's go ahead and write it out since we know what it is. 27 b cubed, okay, and then c squared times raised to the third power, 3 to the c to the 2 times 3, which is c to the 6th, and then we have, and we're going to execute the parentheses down here, and b squared c squared, right? All right, now let's line this thing up. Let's get our numbers together. All right, and let's see. So let's take our 2 and our 27. And remember, you can use a distributive property, commutative property, to move these numbers around to suit yourself, knowing that 2 times b is the same thing as b times 2 and so forth. So first of all, let's put our numbers together. So what we have is we've got 2 times 27, okay? Now let's put all our b's together. We got 2 times 27, then we got a b cubed here, we got a b cubed here, we've got a b squared down here. So what we're going to do is we're going to say, okay, this is b cubed times b cubed times b cubed. Make sure I did all my math right here. B cubed, yep, okay. And then over down underneath, we're going to have b squared, right? And then we're going to then do the c's, put them all together. So I've got c to the minus 4th, c to the minus 4th, times c to the 6th, times c, divide by c squared, okay? Okay, so notice how I've just rearranged this thing to make it easier to group. I didn't put any numbers in the denominator, so what do we got here? If we split this up now into sections, all right? Now I've got my numbers together, I've got one variable together, the b's, and I've got another variable, c's together. Okay, so let's finalize this, okay? So 2 times 27 is, say, 54, right? Okay, what do we got? We got b cubed times b cubed, which is b to the 6th, right? Adding exponents, we're either multiplied, so we add the exponents. And we've got b to the 6th divided by b squared, right? This becomes b to the 6th, and b squared down here. 6 minus 2, using the subtraction rule, is what? B to the 4th, right? And then we've got, it looks like, oh, that's interesting. So we got c to the minus 4 times c to the 6th, and that's going to be c squared, right, on top. C squared on the bottom. What is that? That actually equals, the c's all equal 1. I didn't need my denominator, my division sign here. So it's just 54. B to the 4th is my final answer, right? Because this all, the green all becomes, the green all becomes 1, because it's actually c squared over c squared, which is equal to 1. And so the 1 over here we don't have to write. I mean, you could write the 1 in there just to remind yourself that you had gone through the math, but you really don't need to. So what we ended up with is a final answer with what started out as a fairly complex looking problem is really kind of a simple answer. Okay, when we say simplify the exponential expression, this is what we're talking about. We take our numbers and then we take each variable and then we work it down to something reasonable. Okay, let's see. Let's work one more of these. Let me see if I can find one that looks like it might be fun. Let's do a couple here. All right, let's take a look at. We could do all these all day, right? They're just so much fun. All right, suppose we have 3x cubed. 3x cubed squared times x to the 4th. All right? So let's go ahead and take care of our parentheses. What's that going to be equal? 3 squared is 9. X cubed raised to the x cubed raised to the 2nd power is x to the 3 times 2, so that's x to the 6th times x to the 4th. Okay, and that equals 9x to the, using the addition rule, 9x to the 10th. Okay. All right, let's see. This particular page I'm looking at doesn't have mixed variables, so let's make up one here. All right. All right. So let me, and I'm going to. I won't erase that. We'll just make a new page because as we go through this step by step, we sometimes take up a lot of room. So let's say we have 3 w squared v cubed times 2 w squared times v to the minus 3 all over 2 cubed wv to the minus 2. Okay, well this one's fairly complicated, okay? We're going to have some reciprocal rules, we're going to add addition, subtraction rules, and all that good stuff, okay? But again, in a case like wv to the minus 2, let's talk about this for just a second before we start, okay? When we have something like this, wv all to the minus 2, we can go ahead and carry that out, okay, as w to the minus 2, v to the minus 2, line up our variables and everything. When we have a negative exponent, however, sometimes it's more convenient to go ahead and apply the reciprocal rule first, because this whole group is raised to the minus 2. If we just take it upstairs, it would become WV to the positive 2, right? And that might be a little easier to deal with than doing our negative exponents down here and bringing it out and then doing the subtraction and all that good stuff, right? So there are times when you will look at these and you say, okay, what's easier? What's an easier approach to get this done? Sometimes you'll go ahead and execute where it stands. Sometimes you want to apply a reciprocal rule if it makes sense to do that. So I'll tell you what, let's do. Let's do that. So let's go ahead and use the reciprocal rule first. And so what do we have then? And we're probably, I do still have some issues with negative exponents, but that's not really a big deal. So let's see what this turns out to do. Okay, so 3 cubed is 27. W squared raised to the third power is W to the 6th. And V cubed, V raised to the third power is V cubed. And then we have 2W. Remember, order of operations on this multiplication here. We're going to do the exponent first and then multiply, right? And so we're going to have times 2 squared, which is 4, and W squared, okay? And then we've got times V to the minus 3. And then we can apply this where we brought it from upstairs. Now, remember, when we brought this upstairs here, right here, this one goes away, right? Because we use the reciprocal rule and we took it upstairs. So let's go ahead and finish that out. So what we have here, and I'm going to go ahead and extend this, I've got W squared and then V squared. So I got W squared, V squared. And now we've got everything in the world up there. And down at the bottom then, the only thing we got left down here is this 2 cubed. So down in the denominator, we got 2 cubed, which is 8, okay? So we'll just write this 8. All right. So now let's put all of our variables together and all our numbers together, simplify our life a little bit. And so that's going to be 27 and then 4, right? 27 times 4. And we'll go ahead and write our 8 down here. Okay, so that takes care of it. I'm just going to, sometimes if you, it's a little confusing, you can even do a scratch out, to say, hey, I took care of that, took care of that. Okay, then we've got W to the 6, and then that takes care of that one. W squared takes care of that one. Then W squared again. Okay, that takes care of that one. And then I've got V cubed. Then I've got V to the minus cubed. Okay, and I could take that downstairs, but I think in this case it's just as easy to leave it up there and do the addition. And then we've got finally, so that takes care of that, this takes care of that, and then that takes care of that, V squared, right? Okay, and so change colors in midstream here, but that's okay. All right, so now what do we got? And I think, well, let me scroll down a little bit, give us a little more room. All right, so what do we got? We got 27 times 4, but divided by 8. So this 4 goes into 4 once, goes into 2 here. So I got 27 underneath. The only thing I'm going to have underneath is the 2, right? 27 over 2. Okay, then we got W to the 6 plus W squared, or plus the exponent. W6 times W squared again is 6 plus 2, which is W to the 10th. All right. And then what do we got? We got V to the positive 3 plus a minus 3, that goes to 0, plus 2. And so I've got V squared left over, because these two guys cancel out, right? And there's my final answer. 27W to the 10th, V squared over 2. Boom. All right. That's not too bad, right? It looked kind of crazy when we started, but look where we ended up. Fairly simple expression, okay? All right, so what do we got left here that I wanted to talk about? We did these. I think I'll just leave these up here a minute and let you look at them. Minus 14 x squared over y cubed. there's no simplification to be done there, right? That's pretty much, you have to leave that like it is. I'm not even sure why I stuck these up here. This is left over from another excursion into this topic. Minus 5c cubes. By the way, I do want to point out something. This does trigger me to remember something. These must have been answers. They are. These are answers that I put up on the board for problems that were on a worksheet. Okay. So they don't do much good sitting here by themselves. But what it does, let me clear that page. What it does is remind me to remind you another rule of exponents. It's actually not a rule of exponents, it's just multiplication. But suppose I had minus 3r raised to the third power, right? Now what I've got is, and again, separating these out and applying the parentheses, minus 3 cubed times r cubed. Excuse me. Okay, so what is minus 3 cubed? Well, we've got a negative number raised to an odd power. So I've got minus 3 times minus 3 times minus 3. Minus 3 times minus 3 becomes a positive 9 times a minus 3, which is minus 27, okay? There's a couple of things to tuck in the back of your mind, not too far in the back, all right, is that a negative number, right, raised, in fact, this is a really important little thing to remember, raised to an odd power, okay, odd numbers, 3, 5, 7, 11, all that kind of good stuff, to an odd power will give you a negative number. Okay, that's an important thing to remember. So any negative number raised to an odd power, you're going to end up with a negative number result. All right, and it just makes sense, because you got all these minus signs piled up, minus times minus times minus, and so anytime you have an odd number of minus signs chained together, you're going to end up with a negative number result. Okay, so good thing to stick in your mind and keep it there. All right, so raising to a power. This is a summary of raising to a power that we already did. When raising a number variable with an exponent to a new power, we multiply the exponents. The numbers in the powers must be real numbers, but other than that, there's no restriction. Now, I know you haven't done much with anything other than real numbers right now. We work in the real number system, but there will come a time later in the year in Algebra 2 where we're actually going to do a segment on imaginary numbers, okay, believe it or not, okay? And so, okay, so here we just did some examples again. Here's similar to what we did earlier, showing the odd stuff that we did. Okay, here's another one. Again, notice this example here is another case where we illustrate that here we have a minus 2 here. We're raising it to an odd power. Minus 2 to the 5th gives me a minus 32, okay? And that's where we're going to end today. We will get into exponential equations, which we haven't touched on yet, are very, very interesting equations. Where are they used? Power equations and exponential equations are used where you have very, very high growth rates, or you have what we call decay rates, like half-life of radioactive materials, where things either grow very into a flatter and flatter line as they get lower, or they go up at an exponential rate, which means they're going very, very fast. Okay, so there's a lot of neat applications for these when we get used to the idea of how we operate on exponents. Okay, that's it for today, and thank you very much, and look forward to working with these things some more. And we're going to stop it there. Have a great day.